Alright, so welcome to the 5th data reduction video. This one is for the cross-flow heat exchanger. Alright, so let's go down to the data reduction. Here's some properties that we're going to use, like all of the labs have. Okay, and then, so the first thing we have to do, and we're going to do this for each of our 3 configurations, we're going to plot this temperature distribution versus the time. So basically what we have is R1C1SR. That means we have one row, one column, and a single rod. So that convention, it's shown right here, so you can kind of get an idea of what that means. And then I'll talk about the others. We have R2C3FR, so we have row 2, column 3, and a full row. Then we have R2C3FB, that's row 2, column 3, and we have a full bank. Okay, so on the first one, R1C1, that means row 1, column 1, that's where we would put the copper rod, and so we just have that one single rod, and row 1, column 1. For our next configuration, we have R2C3, so now we're putting our copper rod in row 2, column 3. So row 2 and then column 3 should be right there. Okay, and then let's go back here, and then we're putting plastic dummy rods in all of the other slots within that same row. So FR, full row. And then we have row 2, column 3 again, and then we're going to put in a full bank of rods. So for all of the other slots here, for this cross-flow heat exchanger, we're going to put dummy plastic rods in all of the other slots throughout. Okay, so those are the 3 configurations that we have for this lab. And hold on. Okay, I wanted to find this. So what we also do in this lab is that's spelled wrong, just saw that, and throttle. Alright, so in this lab we had to adjust the throttle to have different airspeeds. So we did it for 10%, 40%, 70%, and 100%. What you would have done in the lab, you would have the pitot tube upstream, and you would measure the mean velocity for the airflow. And then later in the experiment, we'd put it downstream here, where we would measure the velocity profile. So just like we did in lab 2, we would raise the pitot tube in different positions throughout this duct in this case. Okay, so I think I covered everything that you would have done in the lab. Okay, so we're applying that temperature distribution versus time, and we're going to do that for each of our 3 configurations here. And then we're going to fit a linear curve for the data that we have here. So in MATLAB, we're going to use polyfit for that. And we need to find that convective heat transfer coefficient for each run. And we're going to find that from the slope that we have from that temperature distribution. So if I go up here, we have this this linear relationship, so then we can use that to find H using this formula right here. Okay, let's see what else we have. Then we have to calculate the Reynolds number and the Nusselt number for each run as well. So each run, that just means for different throttle openings that we have. Okay, and then later on we're going to plot the Nusselt number versus the Reynolds number, and we're going to do that for each of the 3 configurations. And we're not going to fit it with a power function. Don't need to do that. Okay, and then we're going to calculate the downstream velocity profile, and then we're going to plot the pitot tube position, so that's what we're changing, versus our calculated fluid velocity that we found upstream. And we're going to do that for, again, all of our 4 throttle openings. So if we go to Excel, you have quite a lot of files that I put on Titanium. Here's one of them. So we have This is going to basically match up to our spreadsheet here. So on the first table in Excel, we have this. This is the dynamic pressure head at the upstream position. So we're going to use this head data to find the air velocity. And that's for all 3 configurations and then for all 4 throttle openings. Okay, and then we have this other sheet here, which is downstream, and this is for the velocity profile. So you see we're adjusting the pitot tube quite a lot, from 0 to 122 millimeters. And for this, it's for the full bank configuration, and we're going to do that for all 4 throttle openings. Okay, so again, that's just what we have here. Okay, and then I'll show you 2 more spreadsheets. So basically all the other files are going to look something like this. So we have time here, we have temp 1, temp 2, and temp 3. Temp 3 here, this is going to be the air temperature that you have. And then there's a kind of somewhat confusing aspect for temp 1 and temp 2. In this case, okay, we have one, it's the first configuration basically, where we just have the one solid copper rod. So in this case, I'm not really sure what temp 1 is, and we don't use it, so don't worry about it too much. And I don't know because we didn't do the lab in person. But temp 2, that's going to be the temperature of our copper rod. So if I pull this over here, then I go here, nope, didn't want that. Okay, this. Okay, so we have the single rod right here on the left, and then on the right here, we again have the single rod, but at a different throttle opening of 40% here on the right. So if you look here, in this case on the right, for the throttle opening of 40%, temp 1, that's the temperature for the copper rod. So basically for each of these runs, for each configuration that we have, the copper rod is supposed to start at around 60 degrees Celsius. So basically just want to look for that column. So we see here that starts at 60, so we want to use this column for the temperature data for the copper rod. And over here on the left, this column starts at around 60 degrees, so we want to use this column. So kind of a little quirk, I guess, kind of weird, but it is what it is. So let's go into MATLAB. I hope you're ready to type a lot, because you're going to be typing a lot. Yep. Okay, so what I've done to you is I've finally zoomed in on my computer, because I know some of you have had issues reading the text. Basically, I have a kind of a big monitor. It's 27 inches, so it looks fine on my screen, but if you're looking on a smaller monitor, it's hard to read the text. So I've zoomed in, so hopefully you can read it a lot better now. So we're going to start out by clearing our workspace and all of our text here for the output. Then we're going to specify constants. We have gravity, the air viscosity, air density, air thermal conductivity, water viscosity, water density, water thermal conductivity, the mass of the copper rod, the copper specific heat, the copper rod length, copper rod diameter, copper rod thermal conductivity, and we have the test section width and the test section height. That's for our duct. And then we have some conversion factors here that I don't really need to go over that. It's simple stuff. So we're going to get started just like that. Okay, so now we're going to start out by initializing our arrays. So the first one we have is the convective heat transfer coefficient. We have 12 total values, and really that's for everything that we have here. But we want to keep this just in one vector, just so it's easier when we plot it. So we have 12 values because we had 3 configurations and we had 4 different throttle openings. Then we have the Biot number, again 12 total values, the Nusselt number 12 values, and then for the Reynolds number and our velocity, we're going to kind of put this in a different kind of array here, where we have 4 rows and then 3 columns for our configurations there. And again, that's going to be useful for us when we plot it. It'll make it a little more convenient. So yeah, again, we had 3 configurations for throttle openings. Okay, now we're going to import and sort the raw data. So this is really when we start to get into our typing here. So we're first going to import the datasheet that we had in Excel. And then we're going to import all of the other Excel documents that we have for our 3 different configurations and the 4 different throttle openings for each configuration. So in this part that I have highlighted here, this is for the single rod configuration. We're starting at 10%, then 40%, then 70%, then 100%. And we're going to do that for each configuration. Okay, so I'm going to go through this part kind of fast. Okay, and then we have H range. That's going to be our range for the dynamic head. That's upstream. And so we're going to use this later on to find the velocity, the airspeed. Then we have D range. That's going to be, again, dynamic head, but that's going to be for downstream. This line of code, I forgot to take that out. We don't need this because we're going to import the temperature data for each individual Excel file in this section here. Alright, so let's keep going. So here now I'm going to assign a variable for each of these files that I've imported like we always do. So first off, we're going to import the upstream pressure data and then the downstream pressure data. So H range, let's do this. Wrong one. Oh, I'm blind. Okay, I thought I had MATLAB open here. Okay, so we have this document. So we went from, for H range A4 right here to M9. And then for D range, for the downstream, we started from A3 and then went to E64. So quite a lot of stuff, just like that. Okay, and then for C, that's when we have our first import now for the single rod and 10% throttle. So we're going to import that. We're starting from A2 and we're going to D1135. We have quite a lot of data. Okay, and then I'm just doing that kind of idea for each configuration that we have here. So I'm going to import all of this data. Okay. So now we're going to calculate the upstream velocity for each of our configurations here. So I've, again, typed out quite a lot of stuff. So in this first section, we have the upstream velocity for our single rod configuration. And we're going to do that for each throttle percentage. So for this formula, all we're using is this formula here. So we have 2 times the gravity. The specific gravity for this fluid is just 1 because it's water. And we're going to multiply that by the ratio for the water density to the air density, and we're going to multiply it by our dynamic head reading. So I've just gone ahead and I plugged that in. Okay, so we have 2 times G, and then we have our density ratio, converting from inches to meters, and then multiplying it by our head data. And again, you're going to need to make sure that you are importing the correct columns. So let's snap this over here. Okay, so here's our head data. So we want to make sure for 10% we're using column 2. We have column 2, 30% or 40% column 3, and then so on, just like that. Okay, and then we're going to do that for the full rod or full row configuration, and then the full bank configuration. So again, you just want to follow that kind of format that we have. I was in the wrong sheet. It should have been this sheet. So we're going from column 2, 3, 4, 5, and then all the way out throughout to the full bank here. Okay, let's go back to MATLAB. So we covered all of this. Then we're going to evaluate the mean upstream velocity, and we're going to be using this for our Reynolds number later on. So for this, we want to find the mean velocity. If we go to Excel, we had a pitot tube again, so we were measuring different velocities throughout because we were changing our position. We want to find that mean velocity, so we're going to take just the mean of all of that velocity. So we're going to do that for each configuration again and for each throttle percentage. So at this point, now we're going to compute the downstream velocity. And again, we're going to use this for the radial, or not radial because it's a duct, but we're going to use it for the velocity profile later on. So we're using the same formula that we used up here, except now we're going to take it from B, our variable B here. So this sheet right here where we have, this is for the full bank setting, and we're going for all of our throttle percentages. Okay, so we're going to go ahead and do that. Now we want to import the time data for each configuration that we had. So for all of those Excel sheets, so we have single rod, full row, and full bank for each throttle setting. And for this, let's go to an Excel sheet. We're just going to be taking the first column that we imported. So this is for the time, and you want to make sure you get all of the cells. Okay, so we're doing that for all of that. And then the temperatures, we're going to calculate this now. And take note of this. I already talked about this before, but some sheets have the temperature of the rod, either in cell 3 or in cell 2. So make sure you're selecting the correct one. It's just going to follow what I have, of course, here, because we have the same data. So for this equation, let's go ahead and find that. Okay, so it's just here. We're just calculating this first part. So we have the natural log of our local temperature minus the atmospheric temperature divided by our initial temperature minus the atmospheric temperature. So the first thing we did is we found the mean temperature for the air, so that was in cell 4. And that's the case for each Excel file that we have. It's this cell right here, or this column. Okay, so then we just took the mean temperature because, it's going to vary a bit. And then we used our equation that we talked about. We have the natural log, it's typed out as log in MATLAB, of our local temperature. So again, make sure you're using the correct column and the correct variable that you imported up here. And then we just typed in 60. I guess you could actually put in the exact temperature for each one, because they didn't all start at exactly 60. So for the single rod at 10% percentage for the throttle, that started at 56.3 degrees Celsius. So you can change this if you want, or you can just leave it at 60. Okay, and then we're going to do that for all of our configurations. Alright, so now we're ready to start the data processing of the lab. I guess we kind of already did some up here with the velocity and the temperature distribution, but whatever. This part isn't too long, so you still have a lot of typing to do, kind of, mostly in this part, but you can just copy and paste too, and then just edit it. Okay, so anyways, we're going to start it off by using the polyfit command so we can create our linear curve for our time and temperature distribution data. Okay, so we're going to do this again for all configurations and all throttle openings. So I'm just going to go through this first one here and use the same idea for everything else. So we're doing the polyfit command, then we're going to specify the X data for the time, and then our Y data is going to be the temperature distribution, and then we're going to have a degree of 1. So this first line is for the single rod at 10% throttle. Next one, the single rod, 40% throttle, and then so on. Now we're going to create a time domain. So for this is going to be in seconds. Okay, so we're going from 0 to 600 seconds. And then we're going to use polyval to evaluate the Y value. So we're going to have X and Y. So we have polyval of A01 and then comma X. And then that'll go ahead and give us our Y value that we want to have. Okay, so we're just going to do that for everything right there. Okay, and just like that, we're in the last part of the data processing section. This is all we have to do now. So yeah, there's a lot of typing, but it's a pretty simple lab report overall, or data reduction to do. So the first part, we're going to evaluate the convective heat transfer coefficient, like always, all configurations and all throttle openings, so we have 12 values in total. What we're going to do here is use equation 2.37 to calculate this. So we have our slope that we just found from the temperature distribution versus time. So we're going to solve for H here, and then we can find it. So A critical, or corrected rather, that's going to be our surface area, so pi times the diameter times the length, where we're going to use the corrected length of the actual length of the rod plus this additional part here, because we're treating the tips as adiabatic. Okay. And then M, that's going to be the mass of the rod, and then C, that's the specific heat of the rod. So going back to MATLAB, and we have a negative too, so don't forget that. So going to MATLAB, we're doing A01 of 1. Let me run this code. So we have polyfit up here. That's to give us our line, right? So we have y equals mx plus b. So if we go to A01, we have two values. This first one, that's our slope. So we want to get that. Okay, so that's how we have the slope there, and then we're going to multiply it by the mass and the specific heat, and then divide it by pi times d, that's our diameter there, and then L corrected is right there. Okay, so we're going to do that for all of this. Then we're going to find the Biot number and the Nusselt number, so for that, we're just going to go and use our formulas again. The Nusselt number is up at the top, I think. Okay, so Nusselt number, we are going to use our convective heat transfer coefficient that we just solved for, our corrected length, and then the thermal conductivity of the air. So then we have Ka, that's the thermal conductivity of the air, the corrected length, and then our convective heat transfer coefficient. Then we have the Biot number, so that, I think, is further down. Here it is, our convective heat transfer coefficient, our corrected length, and then the thermal conductivity again, but this time, because it's the Biot number, it's for the copper rod. Okay, and then we're going to iterate from 1 to 12 because we need 12 values, and the only thing changing here is our convective heat transfer coefficient. So we're going to iterate that on I. Let me go back here. So L, that's the characteristic length. I should have not said the corrected length of the rod, but rather the diameter of the rod, which is what we had in here. Okay, so for the Reynolds number, we're going to iterate from 1 to 4. This is going to be for the 4 throttle settings that we have. And then we're going to solve for the 3 different configurations. So we had 3 configurations. So we had the single rod, 5 rods. This should say, well, it's 5 rods, but a full bank. Okay. So we'll do it like that. So we're going to use the Reynolds number formula right here. So we have the density of the air, we have our air velocity that we found upstream, and then we have our diameter, and we have the viscosity of air times 1 minus n times d over h. So n, that's going to be the number of rods that we have. Okay, so for the single rod, obviously we just have 1, so we don't need to put in 1. And then for the other configurations, we had 5 rods, so we're going to put in a 5 right there. And then ht, that's the height of the duct. Okay, so that's it for the data reduction. I guess quickly I'll mention, make sure you're iterating for I for the velocity, and then you have comma 1, comma 2, and comma 3 for each configuration. Okay, so now we're ready to get started on the plot. So the first thing we're going to do are the cooling curves that we have. We're going to have 3 graphs, 1 graph for each configuration. So we'll start out with the single rod. We're going to have our 4 throttle settings. Okay, so the first part we're going to plot the time that we have that was recorded, and we're going to plot our temperature distribution that we calculated. And then on the same graph, we're going to use our polyfit line that we created, that linear curve fit. So we're going to plot our x domain that we created right here. And then we're going to plot all of our y values that we calculated using polyval. And then we're going to use dashed lines for this so we can see how it matches up with the lines, the solid lines up here. Okay, and then like always, make sure that you include a legend. And then I've changed the axis here so the graph looks better. I'll show you what it looks like without it later on. Okay, and then we have the full row right here, so same logic as we used up here. And then our polyfit stuff, labels, title, legend. For the full bank, I'm going to have you do it. Shouldn't be hard at all because we're using the exact same logic as we did up here. You're just going to have to change, to the full bank, and you'll have to change your y values here. Okay, so now let's plot this. Okay, so we have our 2 graphs here. So this is what they look like. If I make it full screen, I can do that. I guess you can actually see right now what I don't want it to look like, which is figure 2 here. So I forgot to adjust the axis on this figure. So if you look at my polyval lines that we created, they keep going and going and going till 600 seconds because that's the time domain that I created. But all of these curves, they don't even go to 600 seconds, so we want to adjust the axis so we can kind of zoom in on the relevant data that we have. So just make sure that you adjust the axis. Okay, so we're in the last part here. We just have to do the Nusselt number versus the Reynolds number, and then the downstream velocity profile. So for this, we are going to have all 3 configurations, and then we're also going to have data markers that correspond to the throttle percentages that we had. So in this first line here, I'm doing it for the configuration of the single rod. So let's go up to our Reynolds number. We had to find the Reynolds number for the 3 configurations, but we also need to keep in mind that we had different throttle settings right here for our velocity that we had. Okay, and then for the Nusselt number, we calculated that here, and that was based off of our heat transfer coefficient, which was also based on our throttle percentage that we had. So For the Nusselt number 1 through 4, that's going to be for our first configuration with the single rod. Numbers 5 through 8, that's for the second configuration with the full row. And 9 through 12, that's the last configuration for the full bank. Okay, so I'll say it one last time. We're in this line right here that's highlighted. We're doing it for the single rod configuration. And then we're getting all of our Reynolds numbers here. And then we're going to have all of our Nusselt numbers and make sure that we're doing the first configuration right there. So if I run this, and we have this, so we have our Reynolds number, and then we have our Nusselt number. And then looking at the graph, we have 4 data markers for our 4 throttle openings. And then make sure your legend is down here, or, up here, wherever. Just don't block the curve. Okay. And then we have our downstream velocity profile. So I'm going to have you finish this off. But I got you started, so all I did was y2 is equal to our variable b, all of the rows in our first column. So essentially, this is just this entire column right here for the position that we had for the pitot tube. So if we go to our handout, we need to plot the pitot tube location versus the fluid velocity that we calculated earlier on. And we're going to do that for all of our throttle openings here. So we're going to have 3 or 4 curves. Go back to MATLAB. So you're going to do that. I'll show you a picture of what it looks like, but first off I want to go over how to save a figure. There's a decent amount of you that are just taking screenshots, and I don't want to see that. It doesn't look good, and it doesn't really look professional. So what you should be doing is go to File, Export Setup, Rendering, Resolution, use at least 300 dpi. And then you're going to click Export, and then you can save that as a JPEG or a PNG, or even better, an SVG, which is a vector format, so it's going to look really good that way. So make sure to do that. Okay, for this downstream velocity profile, it should look like this. So I saved this as a PNG with 600 dpi. I should have adjusted my legend here. You might need to make it smaller, or maybe it'll fit over here. I don't know, but that shouldn't block any of the curves. So anyways, this is what it should look like. And this is a pretty good quality. So yeah, I would recommend doing that. Okay, so we have 10% here in blue, 40% in red, 70% in green, and then 100% in black. So with that, we are done with our data reduction for Lab 5, so only one more to go after this, and then we're done for the semester. So, hope you enjoyed. It felt like this one was faster, so if it wasn't, sorry, but you're done now, hopefully. So I'll see you in the next video. Alright, goodbye.